Okay, so we begin a chapter on Poisson processes, and in this first section we will give a definition and overview some basic operations on Poisson processes. So throughout this section we will consider a measurable space S with the sigma algebra F on it. Okay, and we will assume that it's a reasonably nice space. So in particular, we will be taking product of this space, okay, and we'll compare, or we would like to compute probabilities that random variables on different coordinates, for example, are equal. So we will assume that the diagonal in the product space is a measurable set on this product sigma algebra. Okay, so in applications, the sets or the spaces that we'll consider will be typically a real line or Euclidean space, but one can take, for example, S to be a separable metric space. And then we'll also consider a nice measure on this space. Okay, it doesn't have to be a probability measure, but we will always assume that mu is a sigma finite measure. Okay, and we will also assume that mu is non-atomic. Okay, which means that measure of any singleton or any point is 0. So by the assumption we made above that this is a nice space, every point is actually a measurable set in this space, so we assume that the measure of each point is 0. Now some results will hold for more general measures, but the most important results will be proved under these assumptions, so throughout we will assume that we have this nice space and nice measure. And so given these, now we can give a definition of a Poisson process on this space with this mean measure mu. Okay, so the definition will be a little bit lengthy. And so first, we suppose that our measure mu is decomposed into a series of finite measures. So let's suppose that mu is written as some series of measures mu n, where each mu n has a finite total mass. Now, of course, by the assumption that our measure mu is sigma finite, this holds for some partition of our space, but in this definition we want to start with an arbitrary such representation, right? So in particular, these measures mu n do not have to be defined on disjoint subsets of our space. And throughout this section we will often write each measure mu n as its total mass, so mu of s times Pn, okay, where of course Pn is just this measure mu n scaled by the total mass. In particular, this Pn is a probability measure. Okay, and then given such a decomposition or such a representation of our measure mu, we define a Poisson process with this mean measure as follows. So first we consider independent Poisson random variables. So let the sequence Nn be independent random variables. Okay, and the distribution of this random variable will be Poisson with the mean given by this total mass of the measure mu n above. Okay, so then second, for each n, we consider an IID sequence. These are IID random variables with this distribution Pn. So the measure mu n rescaled to be a probability measure. And then we define or consider this set pi n to be simply this sequence up to the Poisson random variable we defined above. So it's okay, this sequence where we stop at index n given by the Poisson random variable above. So in other words, it's just a Poisson number of IID random variables generated from this probability measure Pn. And then finally, we take a union of these and we call it a Poisson process with the mean measure mu. Okay, we will often also write that this random set that we generated by the above procedure is a Poisson point process with this mean measure mu. So often we'll just write it like that. Okay, and it's also often called a Poisson point process because we really want to view this as a random set. So often we'll forget about all the labelings or all the indices and simply view this pi as some random subset of our space S. Okay, so let's start with a couple of remarks. So in this definition, the first remark is that our assumption that the measure mu is non-atomic means that each of these probability measures Pn is non-atomic. And in particular, all the points that we generated are different with probability 1. Okay, so the first remark is that all points x and L are different. Okay, almost surely, or with probability 1. A second remark is that, of course, the above definition depends on a particular representation that we started with. So in other words, how we represented our measure mu as a sum of these measures with finite total mass. Okay, and one of the main results that we'll prove in this section will show that in fact the definition does not depend on the representation in some sense. Okay, namely, if we view this process pi as a random set. Okay, so we'll make this more precise below, but basically, if we look at this set and we erase all the labels, the order in which it was generated, then the set is indistinguishable no matter how you generate it with respect to which representation. And also, along the way, we will pass through the canonical or through the classical definition of the Poisson process, which looks independent of the representation, but in any case, you have to show that this definition, such process exists. So we have to give this particular concrete definition of the Poisson process anyway. So here I'm just kind of changing the order and start with this concrete definition so that we can go to the properties of the Poisson processes directly, and then we'll come back and discuss why this definition is independent of the representation. Okay, but given this definition, let me actually start with the properties, or more precisely, with some operations that one can do on Poisson processes, which can also be viewed as a way to generate Poisson processes from other processes or from other Poisson processes. So the first operation that we'll look at is called mapping. Okay, so mapping really means that we map our process into another space. So we consider some measurable map f from our space above into another nice space, let's call it S prime, F prime. And then we simply map our Poisson process pi by this map F. So it's just the union as above of the images of all these IID x's that we generated above. Now, if you look at this union, of course, it looks exactly like the definition of Poisson process. So here we have some Poisson n with some given mean, mu n of s, right? And these f's are still IID after this mapping. So we really have to just look at one of them and see what the distribution of this one random variable is. But of course, the distribution of this random variable, it's just the distribution of x, which was Pn, under this map, right? So it's the image measure by this map F. So formally, this union here, or this image of our set, it does look like a Poisson point process with the mean measure, where you simply have to sum over all these ends the total mass that corresponds to the mean of these Poisson random variables, capital N of n, times the probability measure Pn under this image map, right? So if there was no f, this sum would just give us mu, okay, but now it gives us mu image of mu under this map. And so the only requirement that we need is that this is non-atomic, right? If this measure is non-atomic, then each component in this sum would be non-atomic, and as a result, this would be also a definition of a Poisson process for this particular specific representation. Okay, and so immediately we end up with this theorem, which is called the mapping theorem, okay, which states that if this image of our measure mu under this map is non-atomic, so in other words, this map F does not accumulate mass at any particular point, okay, then this set pi mapped by this F is a Poisson process on S prime with the mean measure mu under this map F. Again, here we have a particular decomposition of this measure. So the definition depends on the representation, but again we'll show that it does not in some precise sense. Okay, then the next operation will be the so-called superposition or union. So here we consider a sequence of Poisson point processes, so let's label them by this upper index m. So each one will be a Poisson point process as above, corresponding to some sigma finite measure lambda m. And we have a sequence of these. Now, in particular, by the definition, each of these random sets is generated as a union of some finite random sets given some particular decomposition of our measure into measures with finite mass. But then if we take a union of all these Poisson point processes above, right, it's also a union over both parameters m and n of these finite random sets. And if we define this measure lambda to be a sum of all the mean measures above, right, it's just a sum over all m and n of lambda mn. And of course, the fact that here we have two indices m and n doesn't matter. You can enumerate this pair any way you like, because you are summing positive quantities here. So we can see that this new set pi satisfies the definition of a Poisson point process above for this particular decomposition of the measure lambda, or for this particular representation. Okay, and so automatically we get this theorem, okay, which is called superposition theorem, okay, which states that if you take a union as above, of Poisson processes, it's again a Poisson process or Poisson point process with the mean measure lambda given by the sum of the mean measures. So you can take a union of Poisson point processes and it will automatically be a Poisson point process. Clearly, this new mean measure is a non-atomic measure and also sigma finite. So the next operation that we'll consider is the so-called marking. Okay, and here we will consider some product space, where on the first coordinate it will be our space S, and then you take some other nice measure space on the second coordinate. Okay, and we'll begin with a Poisson point process as above defined on the first coordinate. Okay, so in other words, here on the first coordinate you have a bunch of random points generated as above, okay, which form this random set, which we call Poisson point process. And then we'll define this operation which will map this into the product space and will result in another Poisson point process. And for that, what we will need is the so-called transition kernel or regular conditional probability, and so we'll need a measure defined on the product space through this transition kernel. Okay, so more precisely, let's consider the following measure on a product space. Okay, or on the product sigma algebra on the product space, which will be defined through the Fubini theorem. So mu star of some set C on this product space, so let's say we consider some set C here, okay, we'll define the measure of this set to be an integral over this set of this transition kernel Ks ds prime, and then you integrate with respect to this mean measure mu on the first coordinate. Okay, so more precisely here, for every fixed point S on the first coordinate, right, you consider the slice of this set, and then you integrate on that slice with respect to this kernel K. So this K here is called a transition kernel, okay, or it can also be called regular conditional probability, which is a function of a variable S on the first space and a set, measurable set on the second space with the following two properties. So for all S on the first space, when you view this as a function of a set, a measurable set on the second space, this will be a probability on the sigma algebra F prime. Okay, and then for every measurable set in the sigma algebra F prime, if you view this as a function of this coordinate on the first space, this will be a measurable function on F. Okay, so the definition of the transition kernel, it looks exactly like the definition of a regular conditional probability. The difference is when we talk about regular conditional probability, usually we start with some probability measure defined on the product space, and then we want to represent it in this way using this Fubini representation as a double integral, where we want to know whether this transition kernel exists. And so we proved some theorem in the first chapter when this can be done. But here we go in the other direction and just in this standard Fubini theorem direction. Right? So for example, if this K did not depend on S, this would be a definition of a product measure on the product space. But if you consider K which depends on S in this measurable way like here, the usual standard proof of the Fubini theorem shows that this operation, this double integral, defines a measure on the product space. Okay, and now given this transition kernel, we will define the so-called marked Poisson process. Okay, where what we'll do if we go back to this picture, for every point S here in the Poisson point process on the first coordinate, right, we will consider this slice of the product space, and then we will pick a point here by taking the second coordinate M. Let's call it M of S. It will be marking of this point S to be a random variable from the distribution given by this transition kernel at S. Right? So you have this probability measure on this slice, and simply you pick a point from this probability measure. Okay, and this is called a marking of S. And then we'll do the same thing for every point in our Poisson point process pi. Right, so you pick some random marking for each point here according to this kernel, this transition kernel. And each of these markings will be independent for every point S in the Poisson point process. Okay, and so this will result in this random set in the product space, right? And we'll call it a marked Poisson process. Okay, and we'll see in a second that indeed it is a Poisson process with the mean measure given exactly by this measure mu star defined by this Fubini theorem here. Okay, so again, the marked Poisson process given this probability kernel is just this construction as I said before. So for every point S in pi, you pick a random variable with this distribution given by the transition kernel, and you pick them independently over different points S. Okay, and then you take this process pi star to be the set as above. So the set in the product space with coordinates S and marking of S for every point S in our process pi. Okay, and we just have to notice that this definition here again results in a Poisson point process. Okay, so this is called the marking theorem. That pi star is a Poisson point process with the mean measure mu star defined above, where again let's recall that mu star of any measurable set on the product space is just the integral with respect to the second coordinate first over the slice, and then you integrate with respect to mu on the first coordinate. And by the way, notice that this measure is automatically non-atomic, right? Because the measure of any slice or any vertical line will be just mu at that point on the first coordinate, which is 0. So of course it implies that the measure of any point on the space is 0. And of course the proof of this is completely straightforward, because if we consider this set and just write it out more explicitly in terms of the Poisson point process pi, right, this will be just a union over n, and each point x in this process is replaced by a vector where on the second coordinate you have the marking corresponding to this point. If you look at this union, of course, again it looks like a Poisson process, right? Because this number capital N is still Poisson, and so we only have to look at this particular pair here and say what is the distribution. So these pairs are obviously IID by the construction, and then this pair here has distribution, I will call it Pn of star, where of course just by construction, since you have this independent marking with this conditional distribution given by the transition kernel, right, this will be simply, if you want to compute a probability for any set, you have to integrate with respect to this transition kernel or conditional probability. And on the first coordinate, you integrate with respect to Pn. Right, so again, this union is just a union of Poisson number of IID sequences. So by our definition, it is a Poisson process, and the mean measure of this process, well, you simply have to sum over all n the mean of this Poisson counts, which are the same as before. It's the same, capital N hasn't changed here, right? And then multiply it by this distribution Pn star. But we can see that this is exactly mu star, right? Because if you write this sum on any given set, by definition, when you sum here over n on the right hand side, you're just getting an integral with respect to this transition kernel first, and then the sum of mu n times Pn, that was exactly our measure mu. Okay, and that was the definition of mu star of C. Okay, so it was straightforward to check that this marking construction again results in the so-called marked Poisson process. Okay, so we gave three different ways to construct a Poisson process from other Poisson processes, but again notice that in all of these the resulting process was constructed according to some particular representation of its mean measure. As a result, it will be very important for us to show that a Poisson process in some sense is independent of a particular representation. Now that will be done in the next video, but now let's take a look at one example of a Poisson point process. Okay, namely, we'll take the space to be a positive half line from 0 to infinity, and let's consider the measure on this half line to be of the following form: some constant zeta x to the minus 1 minus zeta dx, okay, where this parameter zeta will be between 0 and 1. Okay, this particular process will come up later in this chapter when we talk about the so-called alpha subordinators. And in some sense, the great importance of this particular family of Poisson processes comes from a special homogeneity in the marking property of this process. So this is done, or it's left to the exercises, so see marking property in the exercises. Now what we'll do here instead is a sort of a preview of the next section. Okay, so in the next section we will consider the sums over Poisson processes, where you take all points in this random set and you sum some function of this set. So here I will only consider this example when you sum all the x's in this process. And what we'll do in the next section is to show when this sum is a proper random variable, so when this sum is finite almost surely. And second, we'll also characterize its distribution by computing either a Laplace transform or a characteristic function. So how do we show for this particular process that this series is finite almost surely? Okay, so to show that this series is finite, let's use the following specific representation of our measure. Namely, let's take the half line and split it into the following disjoint pieces. So from 1 to infinity will be one piece, and then we'll take a union with the union where we split the interval from 0 to 1 into intervals of the form 1 over m minus 1. So 1/2, so starting from 2. So 1/2 to 1, 1/3 to 1/2, and so on. Okay, So let's denote this set as 1, and these sets here let's denote by Sm, okay, from m starting from 2. And so if we take our measure mu and simply write it as a sum over m of the measure mu restricted to the elements of this partition Sm, right, then we can see that on each of these elements of this partition the measure is actually finite. If you check on the first interval from 1 to infinity, the integral of our measure here, well, it's actually 1, so it's finite. And clearly on each of the intervals of the form as above here, the integral would also be finite. So this gives us a particular representation in the definition of the Poisson process. And if you take the sum of points in this random set generated according to this representation, of course, the points above 1, this will be a finite sum simply because the count, right, the number of points on the interval from 1 to infinity, by the definition, it will have a Poisson distribution with the mean 1. So there is just finitely many terms in this sum, so almost surely it's finite. Okay, and then it remains to show that the sum over points x below 1 is also finite, almost surely. And for this we can appeal to Wald's theorem, right? Because if we consider a particular interval Sm from 1 over m to 1 over m minus 1 above, okay, then the number of points, let's call it nm, on that interval, so the cardinality of this set here, is a Poisson random variable with the mean mu of Sm. And the points themselves can be generated as an IID sequence from the measure mu restricted to this set scaled by the measure of this set. So in particular, when we write the sum of points in our Poisson process that fall into this set, Sm, right, we can also represent this by definition as the sum of Poisson number of IID points. Okay, and for this type of expectation, we have Wald's identity, right? When we sum up IID up to some random number, you can write the expectation of the sum by Wald's identity as the expectation of the number, which in this case it's Poisson, so it's just the measure mu of the set Sm times the integral or the expectation, which is the integral of x with respect to the distribution, right, which is just the measure mu restricted to the set Sm scaled by mu of Sm. Right, and you can see here that these constants can be cancelled and you are just left with an integral of x on the set Sm. Okay, and now if you just add these equations up over all m starting from 2, you get that the expectation of the sum over all points x less than 1 is equal to the sum over these intervals Sm, but that's just the union of those intervals is just interval from 0 to 1 of x d mu, which is integral of zeta x minus zeta dx. Okay, and now because zeta is strictly less than 1, this is integrable near 0, and in fact this is equal to zeta over 1 minus zeta. So the expectation of this sum is finite, so that means that the sum is also finite. Okay, and although we are going to give a different proof in the next section for a generalization of this result, one can also follow exactly the same strategy as here, just by slicing the function that you add up in the same way as we sliced the values of x here, and then checking that the sum is finite either because there are finitely many points or because the expectation is finite. But for now, what is left in this section is to check that the definition of our Poisson point process, when we view it as a random set, indeed does not depend on a particular representation of the mean measure. Okay, and along the way we will also pass through the classical definition of a Poisson point process.